but a lot bit funny. Might have been slightly ridiculous, but it's hilarious. All right. Okay, well, you guys ready for another day? We're gonna watch a couple videos today too. We've got some hands-on experiments. We're gonna, play around a little bit.
Ready for another night.
The what?
Ready for another night.
Well, you got a long time till that. So, in the words of my favorite politician, suck it up, Buttercup. There's a politician in, I think it was, I don't know, somewhere back east. He invented a law, or he proposed a law, and that's what he titled it, was the Suck It Up Buttercup law. So that's my new phrase now. Anyways, we are talking about hard drives today. We're going to be looking at mass storage, okay? The what? Yeah, it mostly stores what you want. Ish, right? Within close enough, right? Just makes you really feel comfortable, doesn't it? When they tell you it stores it just close enough. But so our goal today is to talk about hard drives for one. The second thing what we're really going to talk about today is a concept you may have heard of called RAID. I don't know if any of you have heard RAID before. Okay. But it's probably one of the most important concepts you can have when it comes to storage on a large scale, okay, on in enterprise environments. So really, those are going to be our two key topics today. Who knows? Maybe we've got a smaller group. We'll see if we maybe get through it a little faster. I don't know. We'll find out how the day goes, right? Okay. So I want to start off though with a video. Any MythBusters fans out there? Yeah. So we're going to watch some Adam Savage. Talking about, to the right place here, bits and bytes first to give you an appreciation of scale. Then we're going to look at how hard drives work and start talking about the characteristics and concepts and components and all those key pieces that you're going to need to know coming from there. Okay, so let's watch Adam.
Hi, and welcome to Testing. I'm Adam. We're here in your cave, Adam.
We are.
You collect a great many things.
I do.
A variety of interests.
You might even say I collect collections.
That's true. You have a bit of everything.
A bit. Nice.
See what I did?
Well done. I like how you did that. So this is a key thing that I like collecting, which is arcane technology.
Mm-hmm.
And this is a kind of arcane technology very few people are paying attention to. This is a bit.
One bit.
One bit, which means this is one yes or no, 0 or 1 logic gate.
So it uses a vacuum tube on the top.
There's a vacuum tube.
Transistors and resistors and stuff.
Yeah, the vacuum tube is labeled IBM. This is from a 52, 53 series IBM mainframe.
So this is older than everyone in this room right now.
Absolutely.
This is interesting because they could replace it. Instead of replacing the tube, when the tubes would blow, because that was what happened with this kind of memory in the old days, was the tube would blow, you'd have to go in, turn the machine off, find out which one was blown, pull it out and put the new one in, right?
Exactly. And this innovation of being able to pop it out and fix it one bit at a time was actually, I bought the magazine ad that celebrates this unit. I mean, this is like, all this isn't that very expensive.
Look at that computer, it looks like a washing machine.
And this is probably 1 kilobyte, right? This is probably a 1K computer.
And just to be clear, the innovation is it has a handle.
That's it. That's the handle.
There's a handle.
So
okay, so this is 1 bit.
This is 1 bit. Now, this is the second piece of super arcane technology that I bought. The first was actually inspired by, there's a seminal book about computing called The Soul of a New Machine by Tracy Kidder.
Never read that.
It is a it's a thrilling book about the development of the first, I think, 386.
Okay.
Right? And back then,
the first modern processor.
Yeah, the first modern processor. And they were talking about all sorts of things, like somewhere in IBM's lab are binders full of zeros and ones. It's the actual root code in binary in paper form, right?
It's got to be a room full of binders.
So yeah, and so there's they get right down to the nuts and bolts, and you kind of really start to understand them. And at one point, they're interviewing Mitch Kapor, the inventor of Lotus, and the guy started Lotus in the first spreadsheet programs. And Mitch Kapor supposedly had a byte on his desk. And I was telling my wife about it. This was about 8 years ago. And I was like, yeah, he had a byte. It was a byte. Like, how amazing is that? And I went on eBay and I found someone in Schenectady, New York. Of course, it'd be in Schenectady, New York,
of course.
right? and she had a bunch of these for sale, and I bought one. This was not cheap. It was about $350.
Wow.
But this is an original IBM byte, so it's 8
So
bits.
8 of these, 1 bit per tube.
Yes.
I assume each one does a different signal or something like that, and then it all pipes it back into the bottom.
Yes, no, depending,
Yeah.
and perhaps can save its state. The innovation with the byte here, and this is from a 1956 Series 703 IBM machine.
Okay. Perfect naming scheme.
The innovation for this is that it has a little cam lock here, so that you could actually repair the memory 1 byte at a time rather than 1 bit.
So you can be 8 times as efficient.
8 times as efficient. Yes, you can pull this out, troubleshoot it, put a new one in, et cetera, et cetera.
So this is 8 bits, 1 byte.
Yes.
This is what I would say is probably the smallest part, the smallest unit of kind of the modern computer. Right?
Absolutely. And just to be clear, all computers operate on a set of gates that say yes or no, 0 or 1. Right. One state or the other. And that's what these are, 8 of those states, allowing us to, you can represent 1 integer with this.
So the difference, the thing that's changed, is that instead of using vacuum tubes now, we use semiconductors
Yes.
that can be printed very small with photolithography and all sorts of other increasingly advanced lithography every year.
That's within the computing power, and then in memory storage, we stored electromagnetic particles on platens, and then now in flash memory. So let's move on
Okay,
to the
moving,
next.
stepping forward.
Bit,
Okay, this
byte,
is very straightforward so far.
right?
This is 1/10 millionth of an MP3, right?
Right, yes,
Okay.
yes, exactly. This is a gigabyte. This is a gigabyte in 1981. It weighs
So this is 6 years younger than me.
6 years younger than you. It weighs 75
It
pounds.
really does. We got it down off the rack.
It's
It's
3 of us.
really heavy.
Yeah.
And you can't, I don't know if you can see it, but there's, I'm not going to try to tilt it, but there's spinning platters inside here. You can hear it. Listen. Oh,
That's like some dust on it.
sounds like computing. And this is the predecessor to the modern hard drive. What we've seen before was RAM.
Yes.
This is long-term storage.
Long-term storage, spinning platens. These are basically aluminum discs, which actually probably really nice aluminum. I can
I'm
crack it
sure.
open and use it. When I tweeted that I'd received this, I got lots of tweets from people saying they used to have to fix these.
Oh.
Which is like when some part of the mainframe went out. Look, it's a hard drive with 2 handles in order to remove it and swap it out.
This is a gigabyte.
This is a
This was just, people don't appreciate this now. A gigabyte in 1984, 81,
So, yeah, 81.
was a ludicrous amount of storage. My first computer that I bought in 1993, I think had 80 megabytes of hard drive.
No, this is a massive amount of memory.
Unbelievable.
Absolutely.
I mean, this would probably cost a couple $1 million at the time. It was probably very expensive.
I would imagine, it did occur to me that it's also probably riding on a pair of really, really sweet bearings.
Oh, I'm sure there's great bearings.
Right? Like they're meant to spin at like 1,000 RPM for 5 years.
Oh yeah, and then this guy in here has probably got some sweet electromagnets to move the heads in and out. of the right
Exactly.
places.
I can't bring myself to say.
Don't part it out. No, don't do that.
I want another one so I can part it out.
There you go.
You
That's
know
the
there's
thing
going to
to
be
do.
some like really good stuff from my R2D2.
The discs in here each weigh 4 or 5 pounds each. It's
Yeah.
like the one that we used to have in our office. So this was a gigabyte, 75 pounds. It's huge.
Yes. So wait, we should be clear.
We took notes. We did a lot of math.
Gigabyte, byte. Actually, we should do it the other way. 1 byte, 1 gigabyte, 1 billion
1
bytes.
billion bytes. So there are a billion of these guys in here.
Yes.
Well, actually, it's more like 1,073,000,000
Yeah,
something. It's like
exactly.
10 to the 24.
Yes, it is exactly 1,073,740,000
Exactly.
piece in here.
I don't know how they all fit, but now I understand why it weighs 75 pounds.
It would seem, except that we've also got this.
So this is another hard drive. This is something I just carry in my bag every
this
day.
is- now you carry this in your
Yeah,
bag.
it's
And this is 1,000 of these.
yeah.
This is a terabyte. It's 1,000 gigabytes.
So it's a billion, trillion of these.
A trillion of these.
It seems unlikely that would fit in there. We did some more math.
We did some more math.
Yeah.
So here's where it gets kind of exciting. If you wanted to build a modern computer utilizing these
Vacuum tubes.
vacuum tubes, if you just to get a gigabyte would take the volume of that computer would be 1.5 cubic kilometers.
So a kilometer by a kilometer by a
1,000
kilometer.
meters by 1,000 meters by 1,000 meters.
That's a real big block of memory.
It gets better.
Okay.
So if you wanted to store this much memory using vacuum tubes, it would be 1,500 cubic kilometers.
Of those cubic
Yes,
kilometers.
Yes.
So you'd have to have a lot of people running around replacing vacuum tubes.
Could you imagine?
It would be the worst job ever.
1,500 cubic kilometers. It's like bigger than any of the. It's bigger than all the 7 wonders of the ancient world and the modern world combined times a million.
Well,
Like,
and then when you think about the scale of things like Amazon's Web Services Cloud, S3 Cloud,
right.
where they're adding terabytes and terabytes every minute of every day, and you're looking at petabyte and exabyte size capacity, this gets insane.
It totally is completely mind-blowing when you realize how much is actually going on inside your computer just to make it seamless for you.
And play MP3s.
And to play everything. And you think that like our dads would maybe work with something.
My grandmother did.
Did she?
Yeah, exactly.
You know, I met somebody, some of the first real computing in the 20th century was happening under top secret operations at Bletchley Park in England during World War II, while Alan Turing was helping to decode the Enigma.
bomb.
Yes, the bomb, exactly.
Bomb.
And one of the things they had at Bletchley Park were rooms full of women crunching numbers.
Yeah, computers.
And those women were called computers.
My grandmother did in World War II.
Did she really?
So yeah, she was a computer.
Oh.
Not in Bletchley Park, but in other parts of it. Anyway.
So there you go. There's a little computer lesson in my collected random detritus from the
60 years from here to there.
60 years from here to here.
That's amazing.
1 trillion of these in here.
It's amazing.
I'm sure that some of our math is wrong.
Almost certainly.
We will be delighted to be correct.
It's my fault. Send emails to me if we mess up the math.
It's been a long time since I've done notation.
Yeah, no kidding. And imagine another 50, 60 years from now, what this is going to look like to, I mean, it's
Well, given Moore's law, right?
keeps getting smaller,
Yep.
keeps getting faster, keeps getting cheaper.
Yeah.
Thanks, Adam. We'll see you guys later with more from the cave.
Bye, guys.
That's a little bit scary to think about, actually.
It kind of is, isn't it, to think about where we've come from and where we are now? I mean, that drive he's holding up, this video's, what, a couple of years old, 2012. Okay, so this is a little bit older now, right? But just to put it into perspective, that little external hard drive he had, in that same physical size now, you can buy disks that contain 10 terabytes in that same size. Okay, think about that. Just in that short period of time, we multiplied it by a factor of 10 in, what, 5 years? You know, where are we headed next? What's going to happen? Excuse me.
As they had in, storage size, we're going to have terabytes of information in like a thumbprint size.
You can buy it already, that size. I saw a drive the other day. It was smaller than the size of my thumbnail, a thumb drive that had a terabyte in it. Okay, think about that. I mean, from vacuum tubes to a trillion of them in the size of my thumbnail in what, 65 years, if that, 50 something years. That's huge amounts of change. And you're absolutely right. We're only headed for bigger change in the very near future. It's going to just scale up even more drastically. Mm-hmm. They will eventually. Right now, we have no need for that kind of storage on a consumer level, right? Now, when you're on the enterprise level, they're blowing past that so fast, it's not even funny. Like I bought a hard drive setup. It's called a NAS, which is, it's basically a collection of drives for a client yesterday, and we had what, 16 terabytes of storage in that, and that's only projected to last the next 2 or 3 years, and then they'll need to add more. And this is just a dental office. Imagine somebody who's actually using a lot of data. You can't. It's required by law to maintain records for almost a decade in some cases. So, but anyway, so hopefully that gives you a little bit of a for the amount or the scale of change that we have experienced recently when it comes to storing data. Okay. Now today we're going to take a look at hard drives, as I've already mentioned. Now I know sometimes students are like, "Hey, hard drives are old technology. Why are we talking about those things? We're talking about like SSDs and other cool stuff like that." Which, that your textbook has some time or some stuff on that you can go through. However, I want to talk about hard drives because A, the concepts, I mean, a lot of the same concepts will transfer over to hard drives, and B, realistically, they are still the thing that dominates the industry by far over SSDs. Now that's going down and eventually we'll have to change, but for now, hard drives are still the bigger component and they're more difficult to understand. So we're going to put more of our focus on how a hard drive works, okay? Because we're stepping away from transistors and logic gates, now moving to moving parts to a mechanically based storage, okay? So I've got one more video we're going to watch this morning. I know you guys are probably like falling asleep watching videos this early in the morning, but we've got one more video that they're going to talk about how a hard drive itself is connected and some of the, or connected and some of the characteristics, okay?
A home computer is a powerful tool, but it must store data reliably to work well. Otherwise, it's kind of pointless, isn't it? Let's look inside and see how it stores data. Look at that. It's marvelous. It's an ordinary hard drive, but its details, of course, are extraordinary. Now, I'm sure you know the essence of a hard drive. We store data on it in binary form, ones and zeros. Now, this ARM supports a head, which is an electromagnet that scans over the disk and either writes data by changing the magnetization of specific sections on the platter, or it just reads the data by measuring the magnetic polarization. But in practice, a lot of hardcore engineering. The key focus lies in being sure that the head can precisely, error-free, read and write to the disk. The first order of business is to move it with great control. To position the ARM, engineers use a voice coil. The base of the ARM sits between two powerful magnets. They're so strong, they're actually kind of hard to pull apart. Now, the ARM moves because of a Lorentz force. Pass a current through a wire that's in a magnetic field, and the wire experiences a force. Reverse the current, and the force also reverses. As current flows in one direction in the coil, the force created by the permanent magnet makes the ARM move this way. Reverse the current, and it moves back. The force on the ARM is directly proportional to the current through the coil, which allows the ARM's position to be finely tuned. Unlike a mechanical system of linkages, there is minimal wear, and it isn't sensitive to temperature. At the end of the ARM lies the most critical component, the head. At its simplest, it's a piece of ferromagnetic material wrapped with wire. As it passes over the magnetized sections of the platter, it measures changes in the direction of the magnetic poles, called Faraday's law. A change in magnetization produces a voltage in a nearby coil. So as the head passes a section where the polarity has changed, it records a voltage spike. The spikes, both negative and positive, represent a 1, and when there is no voltage spike, corresponds to a 0. The head gets astonishingly close to the disk surface, 100 nanometers in older drives, but today under 10 nanometers in the newest ones. As the head gets closer, it covers less area, allowing for more sectors of information to be packed onto the disk surface. To keep that critical height, engineers use an ingenious method. They float the head over the disk. You see, as the disk spins, it forms a boundary layer of air that gets dragged past the stationary head at 80 miles per hour at the outer edge. The head rides on a slider aerodynamically designed to float above the platter. And the genius of this air-bearing technology is its self-induced adjustment. If any disturbance causes the slider to rise too high, it floats back to where it should be. Now, because the head is so close to the disk surface, any stray particles could damage the disk, resulting in data loss. So engineers place this recirculating filter in the airflow. It removes small particles scraped off the platter. To keep the head flying at the right height, the platter is made incredibly smooth. Typically, this platter is so smooth that it has a surface roughness of about 1 nanometer. Let's imagine that this section is in a football field, American or international. The average bump on the surface would be about 3/100ths of an inch. The key element of the platter is the magnetic layer, which is cobalt with perhaps platinum and nickel mixed in. Now, this mixture of metals has high coercivity, which means that it will maintain that magnetization and thus data until it's exposed to enormously clever, using a bit of math to squeeze up to 40% more information on the disk. Consider the sequence of magnetic poles on the disk surface, 0, 1, 0, 1, 1, 1. A scan by the head would reveal these distinct voltage spikes, both positive or negative for the ones. We would be easily able to distinguish it from, say, this similar sequence. If we compare them, they clearly differ. We always work to get more and more data onto a hard drive. One way to do this is to shrink the magnetic domains, but look what happens to the voltage spikes when we do this. For each sequence, the spikes of the ones now overlap and superimpose, giving fuzzy signals. In fact, the two sequences now look very similar. Using a technique called partial response maximum likelihood, engineers have developed sophisticated codes that can take a murky signal like this, generate the possible sequences that could make it up, and then choose the most probable. As with any successful technology, these hard drives remain unnoticed in our daily lives unless something goes wrong. I'm Bill Hammack, the Engineer Guy.
So essentially, the answer to what you were actually trying to store.
Yep. We use fancy math to say this is most likely what you put here. It makes you really feel confident in your hard drive, doesn't it?
That's reassuring.
Okay. But that's, I mean, and realistically, that's the way a hard drive today works. I mean, and if you think about some of the tolerances he talked about, do you realize just how insane that ball field, you know, 100 yards long, right? Okay. The biggest bump allowed in that football field is 0.3 of an inch. Okay, think about that. 1/3 of an inch out of a football field is the big a bump as you can have in there before something's going to go wrong. I mean, the tolerances on it are so tight that it's almost, to me, it almost seems like a miracle that they work in the first place because of that. So I've got a few hard drives here today. I thought we could pass around one and you could take a look at it, okay? Now this hard drive has been through hard times. It's been passed around by students for a long time, but it'll still demonstrate the key pieces of a hard drive, okay? And then I've got some other ones that we've taken apart with that we'll play with in a little bit. But for now, if we look at this particular hard drive right here, we can see all of the components that he was talking about, right? The shiny bit is the platter, right? That's the thing that holds the actual data itself, okay? It's still very shiny. This one, yeah, it's mostly shiny. It's getting dirty now. It wouldn't work. If we were to spin it up, it would head crash, and it would rip that top layer off down to the cobalt, and it's game over. Then we have an actuator arm, right? Underneath here in the magnets, here we've got a voice coil that he talks about that moves the arm side to side. But at the end, I want you to take a look at is, that's where the read-write head is. You'll see it, this tiny little thing just barely floating over it. It looks like a tiny little square. In fact, it's so close to it, it looks like it's touching the surface of the disk. Okay, so we'll pass this around and you can take a look at it. Doubt it. But if you think about that tolerance, right? We could not even fit a human hair in between that read-write head, let alone anything else. In fact, we erase marker or something like that. We drew on the disk while it was spinning, and as the read-write head moved, what do you think it did to that ink? It ripped it off. Yeah. Okay, think about that. You can't even fit the liquid of an ink underneath it. That's how tight it is. That's pretty crazy. Anyways, let's take a look at the way these pieces and ideas and concepts are constructed. You're going to need to know these pieces and concepts because you're going to be working with them. Even if you're using an SSD, many of the names and other elements like that have remained the same that you have to work with over time, okay? So obviously storage takes place on the platter. That's the thing that holds all of the pieces of information, okay? That's where we put everything, is on the platter itself. But the platter itself is broken down into several important pieces that we need to know about, okay? First off, as we look at this platter, you notice how we have these concentric circles getting smaller and smaller and smaller as we go towards the middle, or getting larger coming out towards the edge, however you want to look at it, okay? The track is probably the first logical piece where we're capable of storing information, okay? we store this data in circles because as a hard drive is moving, okay, here's another one. As a hard drive is moving, this platter is spinning, right? Spinning in a circle. Now, depending on the hard drive, it's going to be spinning somewhere between 5,400 RPMs and roughly 15,000 RPMs. Most stuff you guys have at home probably is 7,200 RPMs. That's the most common stuff you'll see in a consumer-based system because it balances cost and speed. It's slow, but it's fast enough for most people, okay? But as this platter spins in circles, we have to wait for that read-write head to do two different pieces of movement, okay? First off is to select the track, i.e. the distance from the center of the platter, okay? So if we're looking at the platter itself and we're looking for a piece of information that's, say, right here, okay? Let's put it, and we'll call this our read-write head where I wrote that too. Let's put that, okay, here's our head, right? On the end of an actuator arm. And we're looking for this piece of information. The first thing that has to happen is that read-write head needs to move to the correct distance, okay, from the center. We call that coming to the correct track, okay? All right. Once we've come to the right track, though, each two pieces, okay? Each of these pieces are called sectors, okay? So once we find the right track, we then have to wait for the sector to rotate, okay, or the platter to rotate until the sector is underneath the read-write head. Now that's part of the reason why mechanical hard drives are so much slower is because we have moving parts, we have to wait for the arm to get to the right place, we have to get to the head for the right place, then we have to read it, then we have to buffer it, then we have to ship it out across the bus to whatever's waiting for it. Versus an SSD, we can nearly instantaneously read it and ship it out the door. Okay, we eliminate a lot of factors with an SSD. The biggest thing, though, is the fact that there's nothing that's moving inside of it, unlike a hard drive. Okay, so when we look at this hard drive, we wait for the track selection, then we wait for the sector. Okay, now sectors themselves are broken down into small pieces. Okay, well, 3 small pieces. Within a sector itself, we will find a header, data, and trailer, okay? Now, how many of you have taken a networking class? Have you done 2705? Okay, about a little over half of you. So in networking, what's the purpose of a header? See how well you guys remember.
Kind of to give you an idea of what's inside of the blocker.
Yeah. Yeah, and it's very much the same when we're in a hard drive, okay? The header is, as it says, synchronization information, right? To put less fancy terms to it, right? It describes the sector, okay? It describes what's being stored in a computer, okay? Or in that particular sector will be described there, okay? Then we will store the actual data itself. And then once we have stored that, the last thing we have to store is error correction data, okay? All 3 of these pieces are required for the hard drive to function successfully. If any of the 3 are corrupted, it's all corrupted, okay? If any of the 3, as we start stepping into really dense hard drives, where we end up with something like this. This is an Enterprise SAS drive. Okay, but look at the size of the platters here in comparison to that other one we passed around. There's a little bit of a difference. Yet this guy stores 3 times the information of the drive that's over there.
Why?
What do you mean, why? Why does it store 3 times the information?
Why do we need it smaller?
Good, okay, good question. Now, why would we have this platter shrink? I want to throw that out for everybody to talk about, okay? Brandon.
It's to reduce the travel time with the head. When it spins, you have less travel time.
Yes. Yes. So when we make it smaller, we have reduced the biggest wait time in a hard drive, right? Which is picking the track and then waiting for it to rotate. So we get rid of seek time and rotational delay, both at the same time.
And if it's smaller, can we also make it spin quicker?
Yes. This drive will spin at 15,000 RPMs. Okay, versus that guy is spinning it, I think that one's 7,000. Oh, I take it back. This one's only 10K. I must have left my 15 in my office. Well, why is there more chance of it being corrupted?
Well, more chance for bleed, I guess, because it's so dense together. But if one thing goes wrong, it's so small that all of whatever is on that thing is not able.
That generally doesn't happen because as we shrink in a computer, we become more precise. Now, if we'd maintained the same precision we were on a large platter, then that would absolutely be an issue. But the way the read-write heads are going to work in this, because we're dealing with, they've actually constructed the voice coils slightly differently in this drive to handle a higher degree of tolerance. So they're much more precise in the way they function so that you won't have an issue with them. In fact, if anything, this drive is several orders of magnitude more reliable than the other one. But because of that, you get what you pay for, right? How much do you guys think you would pay for something like this? It just came around. Yeah, 50, 60 bucks, maybe $100 if it's really high, if you've got like somewhere in the terabytes range of storage in it, right? Okay, this same drive now, let's come over to this one, an Enterprise SAS drive, okay? This guy holds 300 gigabytes and costs $500, okay? Because you're paying for the technology, right? But to the Enterprise, they'd rather have a lot of disks running less storage than just a couple of disks running higher storage. Because again, it's all about speed is what it really comes down to, right? So if we can split it out across a whole bunch of drives instead, we can overall increase our performance and our reliability. And we're going to talk about that after our break when we talk about RAID, okay? No. No. We still do that in SSDs, very much so.
The RAID?
Yes.
We do the RAID then? Yeah.
Yes. Yeah, well, we haven't explained RAID yet, so give it time. So just bear with us. We got to get a little bit more foundation first, okay? So, but back to the concepts of a hard drive itself, right? So we have the platter, right? Okay. We have the track, we have the sector. Now, one of the elements that the diagram in this book doesn't talk about is it leaves off one important element of a hard drive. In fact, I'd argue that it's a very critical element, okay? Each of these individual blocks make up a sector, okay? Within computers, we use groupings of sectors that we call clusters, okay? A cluster is a group of sectors. A cluster is the smallest addressable portion of a disk, okay? And a cluster will consist of, generally a couple sectors. It'll be a factor of 2, whatever way that it's built out. But most often the time it's somewhere between 2 and 4. But it depends on the drive. Okay, the higher the density of the drive, generally, the higher the density of sectors within the cluster itself. Otherwise, we run out of memory addresses.
Sectors have fixed sizes?
Yes. Yes. And do you notice a relationship between the size of a sector, say here, and a size of a sector here? What's the relationship? Smaller where? Yes. Now, why do you think we do that? Because doesn't that really mean I took something and I stored it, say here in this tiny space, I could fit probably 3 of those out here in this drawing, right? And on a real computer, it's actually significantly farther than that. Why do you think we have that scenario going on?
The center can spin much faster and reads faster. The outer edge doesn't, so you need more information to
Other way around.
other way around.
The hard drive, the outside edges are going to be spinning significantly faster than the inside edges,
Oh,
right? So because the concept is right though, okay? Because that outside edge is moving so much more quickly than the inside edge, okay? Do we need now more distance for the read-write head to pick it up? If you think about it, it's attuned to deal with it at this slow speed here in the middle, and now we're several factors faster on the outside edge, okay? Now we need a lot more space to be able to read it reliably. Okay, so our sectors will change size. Now the amount of data they store remains constant, okay, but the physical consumption of space increases as we move to the edge of the spinning disk. Now, an example of this, if you've ever been water skiing, anybody ever been like water skiing or wakeboarding or kneeboarding or something behind a boat, right? Okay, you get behind the boat and you're going one speed, but what happens is the boat makes a corner, and if you swing out to the outside of that corner. Anybody ever done that before, or am I the only one that likes water sports? You go significantly faster, okay? And in a hard drive, you can be, this outside edge can be doing almost 200 miles per hour in a modern hard drive. Okay, think about it. The data that's here is moving at 200 miles per hour. Yet we have to read these incredibly tiny distances with a thing that's running so close that we couldn't even fit a human hair underneath of it, okay? To give you an appreciation of the tolerances. So yeah, we have to make them larger on the outside because it's moving so much faster, for one. The other factor that comes into it now is math, right? If the amount of math that if the number of sectors on the outside edges are more densely populated than the number of sectors on the inside edges, does it become more difficult to pick the right one? Think about it over time. Let's say I have 8 here, and as I step out, all of a sudden now by I get to that time on the outside, I have 80. They all have a discrete beginning and a discrete end, and I have to read within that window, that tiny little window. And if I can't treat that window straight, what am I going to read? Is it going to mix sectors together? Is it going to potentially miss something and think it had nothing when it was reading the gap in between the sectors, right? Overall, we're asking for a huge likelihood of making mistakes. Now, there are some drives, to be fair, that do populate sectors the same density throughout the entire thing. Generally, they're significantly more expensive, and very rarely we don't really use them because there's not a lot of gain to doing it. We have other techniques that are far more effective at storing large data than by putting more sectors into the outside tracks and the edge tracks, okay? So the other component that we need to know here now is there are a couple of gaps. Okay, notice in between each sector, we have these gaps, and then in between each track, we have these gaps. Okay, why do you guys think we have gaps in between them? Why don't they just, why don't we be really efficient and just make them touch each other? Why do we put gaps?
Data might leak over to whatever it's touching.
Yes. In fact, that has become the enemy of high density drives. We're getting to the point now where you can fit 10 terabytes in a hard drive. You've got maybe 4 platters in there, 3-4 platters in a 10 terabyte drive. But what happens as I start squeezing more information into the same physical space? What's going to happen if I do that? Well, let's just think about it logically, okay? So if I have this much space, and let's just, I don't know what's on here. Let's say there's 50 sectors on here, okay? Instead, I decide, you know what? There's now going to be 100 sectors on here, okay? What's happened to those sectors? They've shrunk. They become significantly smaller. Let's say we double it again. Now I have 200 in the place where I had 50, okay? As they become smaller now, what happens to those magnetic domains? We saw that in the video.
More limited in terms of actual physical space to represent data, and therefore physical particles to contain the magnetic charge without losing data potentially.
Yes. We are getting to the point now where these hard drives are shrinking the density so high, packing them in, making the sector so small, that we're being physically restrained by the number of atoms that belong underneath the head to actually hold the read-write charge. Because if I don't have that magnetic charge, right, and as it spreads out, it will dissipate to surrounding atoms. And as it does that, what happens to my ability to read information reliably now? If I have a gap there, it's fine. I can let it spill over, and it's fine, right? But what if there's no gap? What's going to happen to those magnetics? Yeah, you're going to start writing other sectors and potentially other even tracks that you're going to be manipulating, right, on accident. You are going to corrupt the data, okay? Which is one of the big reasons why we've gone to this partial response maximum likelihood approach, meaning we know corruption is going to happen. There is no way around it. In fact, a very significant chunk of the data on any given hard drive at any given time has been corrupted. But we use math to figure out what it should have been. But let me ask you this. You know, it sounds scary. How many of you have ever noticed your hard drive read something wrong? I'd argue probably never, unless the hard drive itself experienced full failure, right? Anybody ever opened up a picture of your cat and found a dog instead? Well, that's a completely different issue. That's not related to your hard drive, right? You ever opened up say a Word document and found like every other letter missing? You don't notice it, right? Because the computer is so good at this math that we can't see it.
Is this a problem in ISOs?
Well, an ISO is a software-based image.
But isn't it a bit for bit copy of whatever it is that it's storing?
It's what it should have been storing. So as we read off and we make an ISO copy of, say, a hard drive, it's going to use maximum response partial likelihood to calculate the ISO image.
But I was more talking about for like when you're putting it on something for Linux, you have ISOs that you put on.
ISO is simply, it's just a file that represents a disk. That's all an ISO is. So it doesn't matter what you store it on. It doesn't matter what you store on a hard drive. They all experience these same characteristics. It could be an ISO. It could be an image. It could be text. It could be music. It could be a video. They all have the same restrictions. The file type doesn't make an effect.
It's not the file type that I'm talking about. I'm talking about the copying from ISO to an actual thing, though.
All you're doing is storing a file on a disk at that point. An ISO is a file. Okay, it's nothing more complex than that. An ISO is a file. So if you're copying it onto a disk, you're just making a copy of a file onto a disk now at that point. So it's the same thing.
So when we do detect that there is a corruption or an error on the drive, do we try to correct that, or do we just leave it as is?
Generally, we leave it alone and wait for it to be read next time, rewritten again. Because in a modern hard drive, we hold coercivity, we hold that magnetic domain long enough that once bleed off starts to happen in a significant volume, it's going to start affecting a lot of the disk at once, and that's when the hard drive itself will just start to begin experiencing failures. It won't hold those charges significantly. You know, they won't hold it accurately by itself. So we generally leave it alone because we're going to eventually end up rewriting that file anyways. You know, you got everybody, when you use a computer, often you're adding files, you're deleting files, you're defragmenting, you're moving, you're changing. You know, everything's in constant flux on the surface of the disk, and it gets rewritten frequently enough. Now, in some cases, yes, it may be rewritten by the firmware when it notices an issue, but most often it's just left alone. Okay, other questions so far?
We're talking about bad sectors of hard drive ages, and you run a check disk, it likes to find bad sectors and try
Yes.
to, what does it do with the data physically? Does it try to isolate those sectors and not write to them anymore?
Yeah, so in the hard drive itself, okay, so now we've got to add another layer of abstraction to answer that question, okay? So on the hard drive, we use tracks, we use platters and sectors and clusters, as well as another element we'll talk about a little bit called cylinders to handle the physical locating of data within a disk, okay? That's the data on the physical platters themselves, okay? But on top of that now, we're going to add a software layer, okay? When you are working with a disk, there's going to be two things that are going to happen. First thing you're going to do is you're going to partition a disk, which means you are going to prepare it for getting formatted. To hold data. You're going to put necessary preparation. You're going to put boundaries on it so that you can store data that way. You know, does this disk store one thing? Does it store two different drives? Is it three? Is it or whatever? Okay. Then the next thing you do is you format the drive. Now, formatting the drive builds out a special table at the beginning of the drive to tell you where to go find information for files. It's like a lookup sheet. You know, like imagine you ran a warehouse and you had a piece of paper with a map on it that says, well, to find widget A, you got to go to row 4, bin 7, shelf, whatever, right? You go, that locating information, that's what goes inside that allocation table. So when you're doing a check disk or something else and a bad sector is detected, all it simply does is put a special notation on the file allocation, not to use it anymore. So then when it comes time to write data, it's as if it was occupied, it just skips over it and moves to the next available sector instead. Sometimes bad sectors can be repaired because when we repartition, we shift the alignment of where the sectors are on the drive. They're not going to be perfectly lining up the same every time we repartition a drive. So it is entirely plausible that by repartitioning a drive, we can scoot so that those bad places end up in the gaps rather than in the data storage itself. But once it starts to hit a large enough volume, the only solution is to replace the drive, because it means we're starting to lose coercivity and we can't hold the values anymore.
So a sector size is not determined physically, determined by software?
It is determined by the firmware. So yes, it is determined by software. Now it's the size of the sectors themselves is determined by the software written by the device manufacturer, right? So it's burnt in to one of these chips here on the back of the drive. So that part you can't change. Now the cluster size you can change. When you come in and you go to format a drive, you can choose the size of clusters, right? And you can choose that because you're choosing the addressability of the drive. The smaller the cluster size it is, there's very much trade-offs here, okay? The smaller the cluster size is, right? Okay, the more efficient we are at storing information. Now let me explain what we mean by that. Let's say we have clusters. You know, let's say each sector is 256 bytes, just for argument's sake, and a cluster is 2 sectors, okay? That means the smallest addressable unit on this drive is how big? 2 sectors, which is how many bytes? Yeah, we're saying at a computer, the smallest level we can address is 512 bytes, okay? So let's say I have a file that's 400 bytes in length. How many sectors will I consume? 400 bytes. Right. Oh, sorry, clusters I meant, because that's the smallest addressable piece. I'll use how many clusters? One. But I have leftover space. What happens to that leftover space? It's wasted space, okay? So imagine I have a file that's, say, 1,000 bytes long. How many clusters will I use?
2 clusters.
Okay, we'll use 2 at that point. But let's say I have a file that's 1,100 bytes in size. How many clusters do I use? We'll use 3 and waste almost all of the third one, right? Okay, so I end up, the smaller my clusters are, the more efficient I am in terms of space because I end up with less waste, right? But what happens though is we end up with so many clusters, now it takes a long time to read a file because rather than a file being broken apart into several larger chunks, it's broken into much more smaller pieces that end up scattered all over the drive. So I might have A, B, C, D, E, F, G. And what happens to reading that data now? Why?
Because now it's got to read A, then move to the position of B, wait for it to come, then move to the position of C, then wait for it to come. It just has to constantly be moving in order to find one file, other than just having them all be lined up and then just read it all.
Right. So this process, this problem right here that we just described is known as fragmentation, okay? And it is only a problem in mechanical drives like this. Fragmentation is not an issue in an SSD because of why? There's no movement in the parts. I can read it from scattered all over heck and back, and I don't care because I can read it all instantly-ish, right? Versus here, you're right, I have to wait for first the read-write head to select the right track, then I have to wait for it to rotate under the head, okay? And altogether, we end up with a lot of latency in reading the files. So the smaller my clusters become, the more distributed files can potentially be, and the longer it can read them. However, what happens, let's say, you know what, I'm going to be dealing with larger files, so I want to deal with have my cluster be, say, 4 sectors in size now. What does that change about the performance characteristics of my drive?
Want to be able to find stuff faster, but you'll waste a ton more space.
Right. I am trading off access speed and both write speed, both of them. I'm saying I want higher read-write speeds, and I will do that at the expense of wasting space, right? So that I'll end up with a file that's, say, 512 bytes, consuming now 1,024 bytes. It's wasting more space because it has to fit into even chunks, right? I cannot split 2 files within a sector. One sector, or cluster, I should say, one cluster, one file or portion thereof. Okay, does that make sense? And then the file system itself lists where all of these different pieces are, and we just hop from point A to point B to point C to D till we reach the end. Okay. The process of defragmentation now is the idea of rearranging the contents on disk. So rather than being scattered like this, we change so that I might have something like A, B, C, D, E, F, G. Now what's my read time like? Significantly impacted, right? Because rather than now having to wait for both the read-write head to spin in and out, as well as waiting for the platter to rotate to the correct place, I can read that all at once, okay? Now, in older technology, when we were reading data off of a hard drive, we would read data sectors or clusters at a time, okay? And we'd read a cluster, read a cluster, read a cluster, read a cluster, read a cluster. So when I was going to say read just this cluster here, I would just read it all by itself, okay? In modern hard drives, though, because we're getting so dense in terms of the data and high in terms of the speed, we often read data a track at a time, meaning it will read the entire track, use math, figure out what was there, break it apart into sectors and clusters, and feed you just the data you asked for at that point, okay? It just makes you feel warm and fuzzy, doesn't it? All the way around. We just love it. Okay? But does that make sense? Okay? So, again, though, in a hard drive, we're dealing with platters, right? Okay? That are broken down into tracks, which are then broken down into sectors. But logically, we use groupings of sectors called clusters, which are the smallest addressable portion of a drive, okay, that we use to access information on it. Okay? All right. Now, within a drive, it's often the case that we end up with multiple platters like this, okay? Each platter is capable of holding data on both the top and the bottom. We call these surfaces, okay? On each surface of a drive, okay, I am capable of storing now tracks, sectors, and clusters independently of one another. So when that drive is built, we end up with a high coercivity layer being attached to both the top and the bottom, okay? With a heavier, now we put a heavier grade metal in the middle to prevent the magnetics from washing down from the top or into the bottom from each other. So we kind of build a, I hate to use the word insulator because when we think of electronics, it's not quite the same thing, but it's close enough to the concept of like what you put in your house, right? It's to build a barrier between the two, okay? So if I have a drive like this that contains 3 platters, how many surfaces do I have? 6, okay? If I have 6 surfaces, how many read-write heads do I have? 6. How many arms do I have? Yeah, each arm, the read-write arm, that's this guy. We're going to have 6 of these arms. Now, there's a restriction here that matters, though, when that arm is moving that read-write head out, okay? Especially in a situation like this. These arms are physically linked, meaning when one moves, they all move, okay? I don't have the place where my arms are all going different ways in different places at the same time, right? They all scan in and they all scan out at the same time. So they're always on the same track together. No, I could read from 6 surfaces, all 6 surfaces at once, because all 6 arms are once, but I can only really read from the same cylinder at a time. Now, let's define what a cylinder is, because that's a new term we haven't used right yet. A cylinder is, so in the drive itself, we have the track right on the surface, those concentric circles. If we were to take that track on the top and the same location on the bottom, right, as well as all the other ones, so we take that same track, i.e. the same distance from center, on all of our platters, that's where the read-write heads are. I can read on all of those tracks at once because the heads are there, right? Because that arm's moving. I can read from that same cylinder, and that's what we call a cylinder, is if we were to link all of those tracks together, that's the shape we would end up with, right? If I were to try to draw that, that's what we'd end up with. Right, because it would come around like that.
So would it be more efficient if we were able to design something where they could move independently?
Possibly, but you got to think about the side effects now. Because what is it that's keeping those heads? What is it that keeps the gap right here? Do you remember in the video? Well, yes, we're dependent on the drag, right? I.e. the wind resistance that comes from the thing spinning, right? Okay. Now I've only got one thing kind of mixing that. What happens now if I've got 6 things going different directions at high speeds all at once? What is that going to do to the air? It's going to create turbulence, right? And what's turbulence going to do to that read-write head? Okay, and if that read-write head touches the surface, what happens? Head crash, game over, okay? Because again, keep in mind, these are so smooth that you would end up with 1/3 of an inch bump over an entire football field. Okay, so they can't handle even the slightest little glancing, barely blow, it's over. Because it'll just rip it off, because it's moving at such a speed, it will peel those top layers off. And then now that top layer is stuck to the read-write head. So what happens is that arm moves and this thing keeps rotating. It starts ripping off more and more and more until it's done.
Here's what I don't really get.
Okay.
If you can't have, I don't know how to do this. So you've got like data on all 3 of them, right?
Yes,
And
all 6 surfaces.
All 6 surfaces. And if you need to read something, something that's related might be on a different surface, right?
It's possible.
Different spot. And so you couldn't read that at the same time. Right?
Why not?
Well, if the arms are all in a big spot, they're on a different track.
On a different track, yes. A different surface, no.
Is data often aligned on the same track?
We do it on purpose, right? Because if you think about it, right? If I'm going to be writing a large file that's going to consume multiple tracks, would I be better to do several tracks on the same surface or do the same track, if it's available, across multiple surfaces? So we would take the same file, essentially, rather than putting all of the file, say, along here like this, right? We would put, a piece of the file here, and a piece of the file here, and a piece of the file here, and maybe the same thing on the bottom surfaces. Because now I have just increased my ability to read and write by several orders, right? I've become, in essence, if I can use all 6 at once, I'm 6 times more efficient. I can do it 6 times faster because I'm doing it with 6 things simultaneously. Does that make sense? So in a modern computer, we are moving away from the concept of cylinders and instead trying to think of them all as numeric tracks, starting, from 1 to the bot, and then they all just build up as if they were all one contiguous thing. And then the modern computer now knows how many tracks are on a surface, and the operating system, when it's writing data, will attempt to break it apart so that those tracks line up. And ideally, the sectors line up if it can. Now, it often can't happen, especially as the drive becomes more and more fragmented. This concept falls apart. That's why it's a good idea on a rotational drive to fragment on a regular basis. Now, whether that's weekly or monthly depends on how heavily you use the drive, or in some cases even daily. I've got clients that have to do it on a daily basis. Otherwise, it becomes too fragmented, and the data itself, the drive will slow down by sometimes a factor of almost 10.
So here's a question that
Okay.
talking about, 'cause it does include RAID a little bit.
Okay.
If you had multiple drives, so let's say a RAID 1 or something like that.
Okay.
If one of them was fragmented but the others were not, would you be able to defragment one and continue using the others?
No, especially because in RAID 1 they are direct copies of one another. So if one is fragmented, the other is fragmented too. They're mirrors of one another. And in RAID 2, the RAID controller to the operating system, the drives appears as if they were one thing. So we can't isolate individual drives in the array for stuff like that. The operating system, it does them all at once. And then the RAID controller, now rather than splitting just across surfaces, will also split across disks. But we'll get a little bit more in depth with that after the break. Okay? Okay. Any more questions about hard drives and the basic functions of them? Are you guys okay with that? Sure.
So on the other slide that you had, we were talking about so each sector has a specific size,
Yes.
and each cluster, if it was 1024 bit or bytes.
Bytes.
So for the purposes of the user displaying information to the user,
Mhm.
if that sector or cluster isn't completely used, do we say to the user that it's completely used if it does have information in it? Or do we still display the exact information that has been used?
What do you mean display to the user? Because the user is only going to see the contents of their file.
Oh, yeah, but if you select or the amount of space used on a hard drive.
I see what you're saying. So you're saying if I were to, for example, come in here, whoa, that was not the button you were supposed to do, Mr. Penn. And you come on here, we end up with file size and size on disk.
22.1 megabytes, but now is that saying that we're using 22.1 megabytes worth of clusters? Because
Notice the size on disk versus the actual file size. Which one's bigger?
Oh, does the parentheses mean on disk?
This is the size.
Oh, size on
This is the size on disk. So this exact file consumes 23,179,186 bytes for the actual file itself. But to store it, I needed additional space. Yeah. Now this wasted space from size on disk for clarity has other factors beyond simply the wasted space of clusters. They come into it because there's extra overhead and other pieces that come in, but that is a significant contributing factor. So yeah, you end up when you store a data using more space than in almost every case, you'll end up with wasted space with every file you store. Because what's the likelihood of it's going to be perfectly divisible by my cluster size? It's extremely rare, right? Good question. Okay, other questions? Any? Awesome.
As sectors fail, can you see that under like when you're update will that decrease?
The hard drive size will not decrease because technically it's still available space. It's just unusable. So the way the operating or most file systems treat it as if it was full data. So as if it was used space. So you may find that, like, say for example, if you were looking at like the C drive here, you'll find that used space would go up without actually storing more stuff. But the total capacity itself is not going to change. Now, also, just for clarity's sake, the total capacity here, right? Look at this. Notice 500 billion bytes stores 465 gigs. Again, coming down to that stuff that we've talked about, right? But now it also brings in additional factors beyond simply the base 10 factor. Then we add in now the overhead for the partition and the overhead for the file system itself. Both of those now reduce available space beyond the difference between the base 2 and the base 10 calculation we talked about on the first week. Okay, awesome questions. I can see you guys are thinking this morning. I like it.
What is the, I don't know if we have an answer for this or if it's ready for this part of the class, but What is the status of storage when it comes to solid state media? Does it store in sectors and clusters the same way as a hard drive does?
Yes, we use the same concepts. The reason being is all of the software in terms of, operating systems and programs and everything are built on those assumptions. So we wanted the SSDs to have the same basis. Now, some SSDs will use complex internal mechanisms to present one face to the operating system that speaks this language and then use their own proprietary stuff on the inside. But as long as it still speaks in terms of clusters and sectors, it still functions in terms of the operating system. Now, they may choose to ignore that concept entirely and store just the pieces they need without wasted space. And that's up to the SSD manufacturer when they implement the firmware. Some do, some don't. But in all of them, they use the concepts of sectors and clusters because that's what everything is based upon in terms of the software we have functioning today.
So I imagine in the future, a couple decades later, when we're probably not using hard drives, that'll end up changing.
Yes. It's likely that some of those concepts will go away, much like a cylinder has. It's still here, but it's slowly fading away just because modern operating systems don't use it a whole ton anymore. We can use math to figure it out instead. And you'll find as we go on, especially next week, we're going to do some old-fashioned hacking. We're going to have some fun there. Anywhere we can use math instead of stored data, we're going to do it. That subject you guys swear you would never use, right? Yeah, it is. Okay, we are way past break time. Do you guys still want to break, or do you want to just power through and get done? What do you guys want to do today? We got another half an hour or so. Do you guys want to just power through and get it over with? Maybe we'll get out a little bit. It either gives us more play time or get done early. We'll see what happens. Okay, let's do it. I like it. Okay, the last topic we need to talk about today, and then I brought in these drives. I thought we could spin some up so you guys could see these things functioning in person, with the tops removed. Obviously, they're ruin drives the instant, because even that speck of dust, if you look at the light in a projector, you can even see that stuff floating in the air. Even that is enough to cause a head crash. Okay, that's actually, most of that's larger than a human hair even. So all of these drives are trashed, so we might as well have some fun with them, right? All right, let's talk about RAID. Okay, RAID is an acronym that stands for Redundant Array of Independent disks. Okay, redundant array of independent disks. Now, the idea behind RAID is to do one of two and sometimes both things, okay? RAID is not meant to function as a backup. Oftentimes people pretend that it is. It shouldn't be, at least if they're smart, because RAID can fail too. But the idea behind RAID is to either provide protection to data or to provide enhanced availability or advanced speeds, okay? I'm going to just put speed for brevity, okay? The idea behind RAID is to either give us protection or to give us speed. Sometimes both, sure. And each RAID, there's several levels of RAID, and each RAID level will have its own characteristics about what it gives you, okay? Now, the simplest level of RAID is what is known as, in fact, why don't we get a little bit more space here, okay? The simplest level of RAID is known as JBOD, okay? Which stands for just a bunch of disks, which means, let's say, for example, I have 1, 2, 3 drives. Each of them are 2 terabytes, okay? In a JBOD, okay, that simply means we are going to treat them as if I had one really big disk of 6 terabytes, okay? And the RAID controller will be responsible for figuring out the translation of what thing is on which physical disk, finding it and retrieving it, okay? Now, this guy, does he give us any enhanced performance? Does he really give us any enhanced speed or protection? Not really. This one is simply used just for large storage, okay? We call it RAID because technically it is a whole bunch of disks together, but it's not really, okay? The first true RAID level is RAID level 0. Now, RAID is numbered, okay? So, RAID 0 uses a concept known as striping, okay? So, if I have, say, 2 disks, right? And they're each 2 terabytes. In RAID level 0, I will have 4 terabytes total storage. Okay, it's much like JBOD that it's additive, okay? But rather than simply just appending the disks together, we are going to take the data and stripe it, i.e. distribute it between each of the disks. Okay, so I've got a diagram here. Give me a second just to find it. Got to get past the optical storage because I don't really care. Okay. Okay, here is a RAID 0 array. Okay, if I were to store the message, weather report for 14 November, partly cloudy with periods of rain, sunrise 0608. Okay, if I were to store this piece of information in RAID 0, notice I break it down. I put 5 characters on each disk, on each surface, right? And then distributed it across them all. So we end up with the data that is striped, right? Right? So we end up distributing the data in strips across each of the drives. Now, what does that do for me in terms of protection? Does it do anything for protection?
It makes it less so.
It does. It increases my risk instead, doesn't it? Because what happens if, let's say, this drive dies? It's failed. Hard crash, head crash, something, right? Data's gone. What does that mean logically for our remaining 4 drives? They just have gibberish, absolutely. It's unreconstructible data. They might as well have all died. So there's 0 protection in RAID level 0, okay? But what does it do to performance? Okay, how does the increased relationship happen?
Now you don't have to just wait for one thing to move. Now you have it all moving at once.
Yes. So say, for example, I have 2 disks in my array. How much faster will I be at reading and writing? Let's say I have 5 disks. 5 times faster reading and writing because I've distributed it across all 5 of the simultaneously.
5 would make me nervous though with
Mm-hmm.
this issue.
RAID 0 should only be used when you are after performance and are willing to live with a lot of risk. We're willing to live on the edge just a little bit. It's known as RAID 10. Okay. So RAID 0, we stripe. Okay. RAID 1 says, you know what? That's kind of sketchy, isn't it?
Yes.
A little bit. So RAID 1 says, let's introduce a different concept instead that we call mirroring. Okay. Mirroring. Again, I have 2 drives, 2 terabytes total, each drive. But this drive and this drive are linked. They are duplicates of each other. Okay? i.e., they are mirror images. They are copies of anything. So anytime I write something here, it's correspondingly written on this drive. Okay? So my write speed, has my write speed gone up at all? No, but how about my read speed? My read speed is now still doubled because I can read from both drives simultaneously, okay? Because these drives are separate physical drives, do I have to remain linked in terms of track and sector and those read-write heads and where they're located on the surfaces? I don't need to stay linked anymore. I can have one reading here and another one's reading over here. So I can read twice as fast, but my write is still the same.
Right, it has to sync up again.
Or it just, what the RAID controller does is when you're writing, it shoves it out to the buffer of each drive, and each drive just writes it as fast as it can. So they don't link, they don't have to be linked, but they do end up oftentimes fairly closely mirroring each other in movement.
We'll both know what the information is, so when you need it, it'll get it.
Yes.
And so
Yes.
RAID 0 has 4 terabytes. This is only going to have 2 terabytes.
Yes.
More protection, less storage, same write speed.
Yeah, so we've come in here and said, you know what? We're in a situation where I'm not writing a ton, or I don't care if those writes a little bit slower, but I cannot risk anything happening to this data, and I need to be able to read it a little faster. RAID 1 is a great situation. Now, and then let me give you a practical example where this is often used. RAID is heavily, heavily, heavily used in server environments or enterprise-grade storage, okay? RAID level 1 is commonly used to store operating systems and basic things like that. They don't change frequently, but we read the crap out of the files on them all the time. And then we would use a different RAID, such as RAID 5 or RAID 10 or RAID 6 or something, to store the bulk data that we would use for the server itself. But it's often they'll have one array that stores the operating system and those core things that we need. I mean, if they get corrupted, everything goes down, right? And often we read them a lot, but we don't necessarily, you only install the operating system once every, maybe a couple of years, if you're lucky. We just leave it alone, right? And it just runs. So they're great for RAID level 1 to use in that type of a scenario. And then we would use something else like RAID 5, 6, or 10 to store the other data, okay? Now, there are several other levels of RAID, and each of them, so here's a mirrored set, right? Because we mirror, right? We got a pair of mirrors, right? These two are mirrored, and then these two are mirrors of each other, okay? But there are several different levels of RAID, okay? The next levels that come into play are going to utilize now the idea of distributing not just the data, but also now bringing in protection data, and ACC data, such as Hamming codes or parity, depending on the level, and then intermixing that in everything as well, okay? So in RAID level 2 now, what we're going to bring in is we're going to store the data across, say, these 4 drives, and then I'll dedicate 3 other drives now to store just Hamming data related to it. So if one fails, I can reconstruct what would have been there based on the remaining drives that are left in the array, right? However, this is a theoretical level. In practicality, we don't use it. We never really have. Reason being is terms of total storage, it's really horribly inefficient. I mean, look at this. We've got 4 drives for data, 3 drives for Hamming data, right? So we end up, using what? We got 1, 4, 5, 7, 8, 7 drives here.
They all have to act as one drive.
And they all function as one big drive, okay? We have other schemes that aren't so heavy. Hamming is really heavy because it takes a lot of storage, as we talked about, right? When we introduced Hamming a few weeks ago, it's really bulky. So we don't really use it a ton in the practical world. So this RAID level was a good introduction, though, to the concept of, well, what if, rather than either running a high risk or duplicating our data, is there ways we can be more efficient? And that's really where RAID levels 2, 3, and beyond come into place, trying to find mixes in terms of the balance, okay? Let me get to this. This is what we really want to get to, okay? Now, with RAID, what I care about from you guys is I care that you have, you know what RAID is, okay? You know what the general levels of RAID are and what's different between them, as well as you know which ones are theoretical and which ones are ones we actually use on a daily basis, because that's what you need to know for the real world, okay? So I have a table here that not only describes all the various levels of RAID, but we'll also use this to describe whether it is theoretical or actually implemented, okay? So I'm going to put a T next to the levels that are theoretical. Yeah, this is a little bit of both, okay? Levels 2, 3, and 4 are really ones we used to help us make logical jumps, okay? RAID level 2 we brought in with Hamming codes and thought, it's it's kind of inefficient, but this idea is really interesting. So what if we go instead to parity? Okay, and they started using it and starting seeing it, but the reliability could have been better. So again, we said, okay, well, let's find a way to do it. So we'll interleave the data in Stripe, very similarly to level 3 to level 4. Then in practicality, the throughput on it sucked. Okay, so we said, well, let's find out a better way. There's got to be a better way. And we introduced RAID level 5. Now, our RAID level 5 is arguably one of the most common levels of RAID in existence today. RAID level 5 functions by interleaving the data, okay, amongst all of the drives, as well as distributing the data. So rather than storing the parity just on a single disk, as we did in RAID level 4, we are going to distribute the parity information. So say, for example, with RAID level 5, I have 3 drives. That's going to be our minimum, right? So that I can stripe the data and parity information. Right? So that way I could have data split between 2 drives and parity on the next one. The next time I would start between data on drives B and C and parity on A. Right? So that all 3 drives contain a mixture of data and parity all at the same time. What really happens there is I have pretty good reliability. I can lose one disk in that array and rebuild it. No big deal. I end up with, you know, my writes are not quite as good as a single disk, but they're not horrible. Mostly because I'm adding extra data in there now that I'm storing the parity information, but my write speeds are significantly enhanced. So we really get a good balance between performance and cost, okay? It's great for situations, you know, like say file servers where we're not writing real heavily like we would with a database server, but we're reading fairly often. And we need a good balance of protection and good performance. RAID level 5 is an ideal candidate for that situation, okay? RAID level 6 says, okay, well, let's step that up, but what if we double our protection? So rather than having 1 copy of the parity information, we'll have 2 levels.
So it's A has the data, then B and C have parity, and B has data, then C and A.
We're going to have an extra disk now as a minimum. So we'd have to have 4 drives now, okay? So we would end up with, say, A and B storing the first file, and C and D storing parity information. And then later on, we might end up with, say, B and C storing data and D and A storing parity information. It's just evenly distributed amongst all of them. But I'm going to store that parity information now twice. That way, I can handle more drive failures, right? Instead of having just 1 drive fail and being able to reconstitute, I could have 2 drives fail, and I could still rebuild it because I would still have all of the information necessary to rebuild the drive. So it gives us extra protection. But because of that, because now I'm writing more data, again, my writes have gone down. So RAID level 6, we won't use a ton unless we really need a lot more protection, but still need the bulk storage. You might use a RAID level 6. It's less common, but it is definitely used. So probably the second most, well, probably third, because RAID level 5 and RAID level 1 are probably tied for first place. RAID level 10 would be our next candidate, okay, for most used. RAID level 10 is ideal for things like database servers where we are heavily reading and writing, okay, where I need to have increased performance on reads and writes, but at the same time, I need to maintain excellent levels of protection, okay, where I can handle multiple failures throughout the array and still be able to just drop a new drive, rebuild it, and everything functions as if nothing went wrong, okay? So this happens by mirroring and striping, okay? So if we were to take a set, right, that's why it's RAID 10. Sometimes it's easier to think of it as RAID plus 1 plus 0, right? I mirror 2 drives, and then I stripe that data across. Okay, so we're going to mirror and stripe at the same time. So I'll make mirrored copies, but then I might stripe those mirrored sets. Okay, so we're going to need a minimum of, again, now of 4 drives here for something like this. That's the minimum for RAID 10. Okay, because I'm going to say stripe my data between A and B here, but then these other drives, C and D, are going to be a mirrored copy of these 2. Does that make sense? Okay, so it's as if I had just a RAID level 0 here in A and B, but then I'm going to use RAID level 1 and I'm going to make a photocopy of my RAID level 0. So I throw a lot of storage at it, but I don't get a ton of space back. You know what I mean? We use a lot more storage than we have available to us. But because of that, we have better reads than a single disk. Okay, we end up with a little bit of slowdown potentially on writes, but again, that's going to depend on how many disks are in the array. It's entirely possible that we can end up with several factors of increase in both reading and writing, but just not as large. Like, for example, I might end up with 4 times the throughput on reading 4 times on writing and 6 times on reading. Something like that, okay? But it's an increase overall, but I do that at the expense of throwing a lot of disks and not a ton of storage, okay? So for example, with my, that NAS I was telling you about that I ordered yesterday, I put 4 2-terabyte drives in it, in array 10, which means I will have, out of that 8 terabytes of usable storage, I will get half of that. So my client will be able to use 4 terabytes, but they paid for 8. But because of that, we end up with 4 times efficiency for the most part, sometimes 6 for their use case, for what they're going to be doing most of the time. We end up with significant improvements.
So with RAID 10, would you be able to lose 2 drives before?
Mm-hmm.
Or I guess would it be, so if you had 6 drives total, you'd be able to lose 3 drives before that?
Potentially. Now, it does depend a little bit on the drives that fail, right?
If you lose it, for example, B and D, I don't think that you could recover from that.
No. So I could lose A and C at the same time. I mean, A and D, for example, I could lose at the same time, or A and B, or C and D at the same time, but I can't lose both of my mirrors of the stripe, all of the mirrors of a stripe at the same time. So if this guy fails, this guy cannot fail until the A is rebuilt. Does that make sense? Because I can't rebuild from the stripe at that point.
So as long as you have 1 copy of it somewhere, then if that other, the other can fail.
Yes. So there is one that you'll find out there. It's specialty RAID level. It's not an official level, but vendors will implement it, where they'll take and combine RAID level 5 now with a mirrored set. I've even seen where they take RAID level 5 and then stripe it for extra performance. They call that a 50. The 15 is better, where we mirror and a RAID level 5, but you end up throwing huge amounts of disks for tiny storage space. So it's very rare to see, because there's more efficient options, especially if you just keep backups of your data. You know what I mean? RAID should never function as a backup entirely on its own. You know, it's meant for availability and performance and protection, yes, but there should always be a competent backup scheme in use of the data as well for protection. Okay, does that make sense? Everybody with us? All right. Well, should we have some fun for a minute? You guys want to spin up some of these drives and play with them? All right, come up here. You can't see crap from down there. Turn the lights on. All the way. And we can spin them all up just for fun.
You said that they would die. Use that.
Well, they're already dead. I already opened them. I already drew on the one of them with a marker. It's game over for all of the data that's there. So I guess I should say they're dead in terms of ability to store data, less dead in terms of ability for us to have fun. Okay, now what I'm hoping for you to get an appreciation now is how all of these pieces work together, as well as, you know, some of the forces that are involved. So let's try turning on this one first. We'll see what happens. Sometimes they won't spin up, because sometimes the motors jam up once I've opened them up a few times. Let's try you again. Come on. You can hear the motor squealing, can't you?
Yep.
That guy's not going to do it. Come on. All right, we'll try this one then. We'll save the big one for the end.
The big one.
Yeah. This is a little adapter, this SAS adapter, because these are designed for servers. You slide it in. You don't even turn the server off. You slide it in, use it. When something's wrong with it, you push the button, you pull it out. It's called hot swapping a drive. But because of that, we have to use these adapter boards, and they're like $200 a piece to turn them into to do what we're trying to do this morning. So let's try this guy.
There we go.
Okay. So we can see as it spins, and you'll watch the head arm. I mean, that arm's not even moving at full speed when it's twitching like that. Okay. That gives you an idea of the pace that it can move between tracks as it's doing it. You know, this drive would have thousands of tracks. So these movements are very fine-grained as that arm's coming in and out. And you'll notice even on the side of this, we have a little filter. Now, why do you think we would have a filter in here?
Because contaminants could present themselves inside them, and you need to remove them.
Yeah, we want to remove it. So naturally, just because of physics, as the air is spinning, any contaminants like that are going to be shoved to the outside and then caught by the filter. Now, hard drives are built in what's called a clean room. Now, this room it's held under a constant pressure, kind of like an airplane, okay, where they keep it under pressure, as well as there's no static electricity present because everybody's basically almost like they're coated in rubber. You've seen one if you've ever seen like Independence Day. They go downstairs and they're like, "This is a clean room, you can't come in," because even a piece of dust coming in with somebody would ruin an entire production of all of those drives. They would have to rip them apart and start over to guarantee that there's no contaminants at all in the system. And then these drives are designed to just do what this guy's doing. This guy, he's spinning, but why is his arm not moving? He's not been asked to move, right? So these arms just kind of get there and they just sit there, and this drive will spin like that for a decade or more, okay? And then the arms will just move, and that head, you can see it floating right there. In fact, if you get down and close to it, you guys can see that head is just floating just above it. Now, this head has crashed several times because I took a marker to it. In fact, we can try putting a marker to it again if you guys want. It might do it.
Oh, dear.
It's always worth a shot, right?
Which way does it spin?
Oh, did you see that? Did you guys see the ink disappear as that head moved? Look, you see the line in there, that stripe that it's cleaned off with that read-write head? Because that head is only just barely on the side, and it's only reading a piece of it. Yeah, the head might be this big, but it only is reading that tiny little thing, okay? We have to use a bigger skid to keep it clear. See that? You see there's a stripe in it now? I didn't put a stripe in there. I can't maintain constant pressure as I moved, but that read-write head is so close, it's peeling the ink off, and it's mad at us now. It's peeling the ink off. Okay, think about it. I mean, is that ink something you guys would think of as thick? Yet it's ripping it off because it is that close together. Let's see if it'll spin up. We might have killed it. Oh,
Nope,
here we
there
go.
You're so mean to it.
See, I can't even write it on that outside edge because it's just ripping it off as I try to draw under there. I can write in here all I want.
Nope.
But that's how tight these heads are, okay? Now, to give you an appreciation of how fast this sucker's moving, we're going to do an experiment. You guys want to kind of stand where you can see, but where toes are going to be clear.
Oh, dear.
Okay? Now,
I'm a little bit.
I have been hit by these, and it doesn't really hurt if you've got shoes on. If it hits bare skin, it hurts.
Oh, dear.
Okay? We're going to spin it up and shoot it down the carpet here. We'll spin up a fast one. So you might want, you can slide to this side. You might even want to just kind of slide up so you're in this gap over here. So we try not to hit anybody. And if it comes at you, don't kick it, please. I had a student kick it one time, and it flew up and almost took another guy's head off. So it's not as dangerous as it sounds, but, I got to cover my butt too, right? So in the platter, in this particular hard drive, let's get the adapter board reinstalled here. Come on. Oh, you're going to want it upside down. Come on. There it goes. Okay. Now, in addition to the platters themselves, okay, we have these rings. You see these little tiny rings, okay? These functions as spacers. That's the distance that's in between each platter in a hard drive like this. There's a ring.
Very small distance.
Very small distance, right? This drive here would have originally had 3 platters in it. We've taken them all out but one. As you can see, we've abused it heavily. It's dented, it's chipped, it's scratched, okay? Now, notice there's no drill points for this platter, okay? It slips on the cylinder. Now, I don't have any holes to mount it, right? Okay? The way that a hard drive works is we're going to slip it over it, and then they use, if you look at this one, you can see how we have this bigger ring around the outside of the cylinder here, okay? And again, on this one, they clamp it, and they squeeze it really tightly together. In fact, you can see on the edge of this drive, you can see the ring, the pressure, that it's dented the metal from where the compression ring was on it originally, because that's how it grabs onto it and spins it. It squeezes it really tight and holds it that way, okay? So, now I got to remember, I don't remember which direction this guy spins.
That's not good.
We'll find out if I shoot myself in the foot, right? Okay, now it's a little bit loud, it's not bad, but we're going to spin it up. This guy's spinning at 10,000 RPMs. Now, I think in consideration, that drive there we just looked at, I think was 7,000 RPMs, maybe 5,000 RPMs. Real expensive drives in a server are 15,000 RPMs, okay? Which, I don't know about you guys, I can't even really I mean, somebody says 15,000 RPMs and I go, that's a really big number.
Yes.
Woo. Okay, hopefully this will give you an appreciation for what 10,000 means, and then you can just scale it up significantly.
Yeah, just imagine about that.
Oh, it fell off inside. Don't do that yet. Coming this way.
That was very startling.
So we gotta go like this. There we go.
That was very worrying.
Yeah, nothing to be afraid of.
Oh,
There you go. It's hard to get out. Notice it's still standing up against the wall once it gets there. Okay? Yeah, now let's find him. Let's do it again. Does that give you an appreciation? Did you see how fast that sucker shot out of there? I mean, it can go. I did one once. Have you guys been on the main campus where the CS building is, right? Where'd the other spacer go?
I have it here.
Oh, okay. We've got the other one here. We're good then.
we haven't been able to find the CS building.
So, you know, we have that long hallway kind of by our offices for those of you who've been there. I shot it from sales, where the farthest end of that, all the way down into our offices. It hit the wall and stood up still. Okay, that's how fast this this piece of metal is spinning. Got to turn it off because it's sitting here spinning away happy and empty. One year, some students built a jump out of 3-ring binders. I'll tell you, it's really hard to aim. Hit that jump. Is it still standing up? That one didn't get quite full speed before it shot. Kind of had an early release there.
We should try to build a launcher out of that one.
It's kind of fun. I'm not gonna lie.
I'm sure that you could manufacture something to launch that.
I probably could. I should. So you see that thing skip? It hit the tip of your toes, and that thing shot up like 3 feet. Do it again, shall we?
I wonder how quickly it slows down as soon as it hits the carpet.
Significantly.
So
Because to give you an example, like if we were to go do it on the tile outside, it just stands there, and really it only goes maybe 4 feet because it's spinning so fast it can't even get traction on the smooth surface of the tile. The carpet's better because it grabs traction and shoots like a rocket. Come on, grab it again. No, it stopped. The motor on this is getting mad at me for doing this.
That's why we need to figure out a way to manufacture this to get it to work.
It's more fun when it's a real hard drive that you've taken apart, though. Come on. I do. I used to be able to get them from the data center. But now with protection laws to the data itself, it's harder. They can't give them to me. They have to physically destroy the disk. And it's hard to convince the department to blow $300 on something I can take apart and use for a couple of semesters before. Ow! Son of a. Semesters before I have to buy a new one.
I've got a broken one if you want. I don't know whether it's up or not. I just can't read it.
See, now it goes because there's no platter on it. Let me try reducing let's take a spacer out and see if maybe a little less weight will make it play one more time. Come on.
You can do it, hard drive. We believe in
You could do it, little friend.
And don't shoot the teacher again.
Sounds like it's laughing at me, doesn't it?
Just like, ha! No. Hard drives were not designed to do this.
No, they were not.
Aw.
We almost had it. I don't know, it might be giving up the ghost. At least we got a couple of good launches out of it, right? That first one was really good. I wanted to get a couple of those. Stupid thing.
Oh, that one sounded interesting.
Oh. Ah. Here we go. We're up to speed. Although with the spacer, there goes. Look at him. Did you see him bounce and stay standing up? Bounce, bounce, still standing up and over. Oh, here comes another one. Out the door. Okay, that one was awesome. That's more like what I'm looking for right there. But, I mean, think about it. This little metal thing is standing up against a wall 20 feet away, oops, and standing up for 5 or 6 seconds. That thing is, I think the sucker's moving, right? But hopefully that gives you guys a little bit of an appreciation, though, for what it is we're talking about and how these things work and the components that are inside of them and how they function and the speeds and the tolerances and everything it takes to kind of mostly store the data you ask it to. Okay? All right. Any questions we need to take care of before we let you guys go for the weekend? Okay, don't forget your quiz. Your quiz will cover the topics we've talked about with I/O last time, hard drives, and RAID today, as well as the never-ending nightmare known as conversions, right? Okay, so don't forget that's due Sunday, and we will see you on Tuesday. Next week, we're going to have a little fun. We're going to do some old school